Hello, welcome to the online course on analog integrated circuits. In today's class, let us start discussing about one of the fundamental building blocks in electronic technology, that is phase locked loop. This circuit has many applications, mainly in communication systems like frequency synthesizer, FM demodulation, etc. Let's understand what is meant by phase locking. It is generally producing a signal of having same phase with the incoming signal. Suppose we have a signal A into sin omega ct plus 5. Here this term is the phase, and this can be time varying function or not. So this is the phase, and we want to lock this overall phase, that is the aim of a PLL circuit. Within this there are two constituent parts. One is frequency, another one is the phase. For actual phase we are generally using. In these terms, one of the term can be time varying, or both of them can be varying with the time. Hence, we have to extract the time varying term to synchronize the locally generated signal with incoming signal. So here we will have a feedback. With that feedback, we will try to minimize the phase error between incoming and locally generated signal. That's the overall principle. Here, principle is very simple. Suppose I have a phase which is incoming. So let's say I have a sinusoidal signal which is coming with an incoming phase of theta I of t, and locally I will be generating some theta naught of t, and my target should be that this difference between theta I of t and theta naught of t must go to 0 or a constant. So I need to create a feedback loop so that the error, which is the phase error, must go to 0 or a desired value. Here you should remember one thing. In a signal A into sin omega ct plus 5, this whole term omega ct plus 5 is the instantaneous phase of the system, and from this we can find the instantaneous frequency by just differentiating the whole term with respect to time. So if this phi term is constant, that is independent of time, then in a PLL circuit we need to lock the frequency omega c. On the other hand, if the frequency is fixed and it is known, and the term phi is a time varying function, then we need to lock this phase term. Suppose both frequency and phase are time varying function, then there is no need of discriminating these two terms. Instead, consider this theta of t as a whole, and we need to lock this instantaneous phase. Let's look at the PLL circuit. Here is the circuit which consists of a phase detector, a low pass filter, amplifier, and a voltage controlled oscillator. This phase detector is basically a multiplier that produces the signal having frequency components Fin plus F0 and Fin minus F0. The high frequency component, that is Fin plus F0, is removed by the low pass filter, and the difference frequency component, that is Fin minus F0, is amplified and then applied as a control voltage Vc to this voltage controlled oscillator. The signal Vc shift Vc of frequency in a direction to reduce the frequency difference between Fin and F0, or the phase difference associated with those frequencies. Once this action starts, we can say that the signal is in capture range. The VCO continues to change the frequency till its output frequency is exactly the same as input signal frequency. Then the circuit is said to be locked. Once the circuit is locked, the signal of frequency F0 of VCO is identical to the input signal having frequency Fin except for a finite phase difference phi. This constant phase difference phi generates a corrective control voltage Vc to shift the frequency from F0 to Fin and thereby maintain the lock. Once the circuit is locked, PLL tracks the frequency changes of the input signal. Basically, the PLL goes through three stages. First one is free running, in which the circuit produces an output signal of having frequency FR. The circuit will be in this stage when there is no input is applied. So the frequency of output signal determined by the external timing capacitor and external resistor. In the capture range, the circuit will start to vary the frequency of the output signal due to the difference in phase or frequency between input signal and VCO output. Each successive cycle causes the VCO frequency to move closer to input signal frequency. Then the difference in frequency becomes smaller and smaller, and the phase detector output will have larger DC component. This process continues until VCO locks on to the input signal and the difference in frequency becomes zero and a constant phase difference. And the last stage is locked or tracking stage, in which the PLL tracks the frequency changes of the input signal. Whenever a change occurs, the system again moves into capture stage. Let us familiarize with the important terms which characterize the performance of PLL, that is capture range and locking range. Capture range is defined as the range of frequency centered about the VCO free running frequency over which the output signal frequency of the VCO can acquire lock with the input signal frequency. Once it is locked, there will be a limited range, basically more wider than capture range, over which the circuit can maintain the lock. This range of frequency is known as locking range. Okay, so let me stop here today. We can continue in the next class with applications of PLL. Thank you.